As night falls and the world around you begins to soften, let us drift together into the gentle hush of history, into a time long before electric light, before modern maps of the cosmos, before even the written word. We begin beneath the same sky you see tonight, an ancient ink-dark canvas scattered with stars, planets, and patterns too vast to name all at once. This is the story of how humanity first looked upward, and how those early glances became questions, and those questions became the study we now call astronomy. Imagine, if you will, a night in the Paleolithic era. There are no cities, no calendars, no clocks, only the slow breathing of the earth, the crackle of a fire, and overhead a brilliance that speaks in silence. Our ancestors gaze upward, mesmerized by the moon's changing face, the shimmering river of the Milky Way, and the patient wanderers, those mysterious lights we now call planets that do not move like the others. These people cannot name what they see, yet already their eyes are measuring, their minds are wondering, across thousands of years and all corners of the world. From Mesopotamia to Mesoamerica, from Egypt to China, from the high Andes to the open steppes of Central Asia, humans begin to track the sky. They carve notches into bones, draw stars on cave walls, and eventually erect monuments that reach skyward stone circles, observatories, temples aligned to solstices and equinoxes. These are not merely acts of wonder. They are tools. The sky is becoming a map not only of space, but of time. The earliest records we find speak not just of stars, but of stories. The night sky becomes a mythological tapestry. A lion prowls the heavens. A scorpion stings in autumn's chill. A hunter chases prey across the sky, forever frozen in mid-stride. These constellations are more than decoration. They are memory keepers, time markers, navigational beacons. To tell the stars is to tell the seasons, to guide the harvest, to steer a ship, to mark the sacred days. As we move deeper into this story, you'll come to see how early civilizations used the heavens not simply to wonder, but to govern, to plant, to pray. Kings consulted eclipses. Priests read omens in the planets. Farmers waited for Sirius to rise before sowing seed. Slowly, what begins as observation becomes system, and what begins as system becomes science. But this story is not a straight line. It drifts, loops, pauses. It is shaped by war, religion, geography, and trade. Cultures rise, and with them, their knowledge of the stars. They fall, and often, so too does what they knew, only to be rediscovered generations later under a different sky, in a different tongue. You will hear of Babylonian star charts etched in cuneiform on clay, of Egyptian temple walls where shadows mark the solstice, of Chinese records so meticulous they track a comet's path over centuries. You will travel with Polynesian wayfinders who sail by starlight alone, and Greek philosophers who imagine the cosmos as a grand ordered sphere. Later, you'll meet Islamic astronomers who preserve, translate, and expand on ancient texts, creating observatories more advanced than anything in Europe for centuries. You'll see how the torch of knowledge passes silently from one hand to another across continents and millennia. As you settle into sleep, let this story become your sky. A slow arc through time, dotted with questions and discoveries. This is not only the story of ancient astronomy, is the story of attention, of wonder, of the human desire to understand what lies just beyond reach. So close your eyes, breathe, and slowly let the stars come closer. We begin our journey now, beneath the eternal sky. Asterisk, before writing, before farming, before even the first cities, there were stars. Long before the wheel, long before metal tools, our distant ancestors looked upward in quiet awe. The night sky was not polluted with artificial light. It was vast, overwhelming, and deeply present. For the people of the Paleolithic world, hunter-gatherers moving across plains, forests, and river valleys, this sky was a companion, a constant presence above their campfires and open shelters, and unlike much of the changing world around them, the stars followed a pattern. Asterisk, imagine yourself in a Paleolithic camp tens of thousands of years ago. The air is cold. Wind rustles through tall grasses. You sit beside a fire, your only warmth, your only defense against the night. A few others are nearby. Silence dominates, except for the occasional crack of wood or distant howl above you. Infinity. The sky is so clear, you can see every glittering pinprick. The Milky Way stretches across the heavens like a pale river. Your eyes, accustomed to the dark, begin to notice patterns. A curved hook here, a cluster there. Night after night, you see them again and again, but not always in the same place. Some move, some return after long absences, some vanish behind the horizon, only to reappear months later. These movements aren't just curious, they're meaningful. Asterisk, there is no writing yet. No books, no scrolls. So how do you remember the stars? Through repetition, through carving, through art. In modern-day Germany, a small piece of mammoth ivory now known as the Löwenmensch, or Lion Man, was carved around 40,000 years ago. While its meaning remains debated, some scholars believe figures like these could have had cosmological or spiritual significance. More telling, however, are early artifacts like the Blanchard bone found in France. This curved piece of bone is marked with carefully cut notches. Some researchers propose it may represent a lunar calendar, a way of tracking the phases of the moon. If so, it would be among the earliest known attempts to measure time by the sky. The moon, after all, was the easiest celestial body to track. Its phases were obvious. The full moon flooded the landscape with silver light. The new moon left the world in darkness. Over time, early humans may have noticed the connection between moon phases and other natural events, animal behavior, tides, or fertility cycles. Cave walls and star stories in deep caves like Lascaux in France and Altamira in Spain. Prehistoric people painted animals, bison, horses, deer along the walls. These paintings are famous for their detail and age, dating back around 17,000 years. But hidden among these images, some researchers believe, are star maps. In one chamber at Lascaux, a painting of a bull is accompanied by a pattern of dots. The arrangement closely resembles the Pleiades star cluster, also known as the Seven Sisters. If this interpretation is correct, it suggests that Paleolithic humans weren't just tracking stars. They were embedding them in their culture and mythology. Even in this early era, the line between science and story was not clear. The sky was both a clock and a canvas, both a guide and a god. The seasonal dance. As millennia passed, humans became more attuned to cycles not just of the moon, but of the sun and stars. They noticed that certain stars appeared only at certain times of the year. Some marked the coming of winter, others the return of spring. Migrating animals, blooming plants, and changing weather patterns all seemed to align with the heavens. In the Upper Paleolithic, long before agriculture, people may have already been tracking solstices, the longest and shortest days of the year. Using the angle of the sun's rise, or the length of its shadow, they could mark the turning points of each solar cycle. This wasn't just useful, it was sacred. Over time, these natural events became the foundation for rituals, stories, and the earliest forms of religion. Shamanism and the sky. Many early societies viewed the sky not just as a physical space, but a spiritual realm. In cultures around the world, shamans or spiritual leaders acted as intermediaries between the earth and the heavens. During rituals often involving trance, fire, and darkness, they would call upon spirits or ancestors, many of whom were imagined as residing in the sky. In this way, stars became more than light. They became beings, guardians, ancestors, gods. This spiritual sky would evolve over time into mythology, then into astrology, and eventually into observational astronomy. But its origins lie here, around fires, in caves, in dreams, megaliths, and sky stones. As the Paleolithic era gave way to the Neolithic around 10,000 BCE, humans began to settle. They built permanent homes, domesticated animals, and planted crops. With farming came a new dependence on the seasons. Knowing exactly when to plant, harvest, and store food could mean the difference between feast and famine. And so, people began building structures, not just for shelter or worship, but to track the sky. One of the earliest and most famous of these is Nabda Playa, located in the Nubian desert of southern Egypt. Long before the pyramids, people here erected large stones in a circle that aligned with the summer solstice sunrise. Dated to around 6000 BCE, Nabda Playa may be one of the world's first astronomical observatories. Similar sites would soon appear across the globe: Stonehenge in England, the Gozek Circle in Germany, and many others. These megalithic monuments marked solstices, equinoxes, lunar standstills, and even the rising of bright stars like Sirius. These were not random stones. They were calendars, compasses, temples, a legacy written in stone and sky. By the end of this chapter of human history, astronomy had no name, but it had a place in the minds of early people. The heavens were alive. They told stories, they marked time, they offered guidance, mystery, and meaning. And even though no written records survive from these distant days, their influence echoes in stone circles, carved bones, and painted caves. The seeds of science were already sown. As we leave the Paleolithic behind, a new age dawns. Civilization begins to rise. Cities form. Writing is invented. And with it, the sky begins to speak in a new way through tablets, scrolls, and texts. Next, we'll journey into the ancient cities of Mesopotamia, where priests climbed ziggurats to read the stars and kings consulted the heavens before war. But for now, let the fire fade. Let the stars swirl overhead, and rest in the stillness of a sky that has always been there. Asterisk. The land between the rivers the Tigris and the Euphrates was unlike any place before it. Here, in the fertile plains of Mesopotamia, the first cities bloomed, your Uruk Babylon, and others, alongside writing, government, and monumental architecture. Another profound achievement began to take shape: the systematization of the sky. It was no longer just the realm of myth. The heavens were becoming measurable, chartable, predictable, and yet they still spoke the language of gods and omens. For the first time in history, we can read what people thought about the stars. Around 3000 BCE, the Sumerians invented cuneiform, a wedge-shaped writing system pressed into clay tablets. As this script evolved, it began to record more than trade and law. It began to record the sky. Thousands of clay tablets, many preserved in the ruins of Babylonian libraries, revealed detailed observations of celestial events, the phases of the moon, eclipses, planetary risings, and more. The Malapin tablets, dated to around 1000 BCE, compile centuries of astronomical knowledge into one extraordinary record. Here, the heavens become a formal system. In the center of every Mesopotamian city stood a towering structure, the Ziggurat. These stepped temples rose toward the sky not only as places of worship, but as observatories. Priests, known as Baru or Tupsharu, were the astronomers of their day. They climbed the ziggurats at night, watched the stars, recorded patterns, and interpreted what they saw. But their purpose was not purely scientific. In Mesopotamia, astronomy and astrology were inseparable. Celestial events were messages, omens from the gods. A lunar eclipse might signal danger to the king. The sudden appearance of a bright comet might mean an enemy's rise. These interpretations were collected in a vast body of texts called Enuma, Anu, and Lil, a series of over 70 tablets describing celestial signs and their meanings. The Mesopotamians understood the moon intimately. They divided the lunar month into 30 days, each day associated with a specific star or constellation. This lunar calendar was remarkably precise, accounting for the waxing and waning of the moon with religious and agricultural significance. Over time, adjustments were made to synchronize the lunar calendar with the solar year. Special months and intercalary months were added when necessary. Based on astronomical observation, this practical attention to cycles allowed them to coordinate festivals, planting, taxation, and governance across vast city-states. The Babylonians organized the sky into 3 great paths: the path of Enlil, the northern band of the sky; the path of Anu, the central zone; the path of Ea, the southern band. These divisions were more than symbolic. They allowed astrologer priests to map where specific stars and planets would rise and set across the seasons. They also developed star catalogs, identifying dozens of constellations and individual stars. Some of these star names, like Shulpi, Jupiter, or Nibiru, possibly Mercury or a pole star, appear again and again. Eventually, the Babylonians created a recognizable zodiac, a 12-part division of the sky, each associated with a set of stars and a span of the ecliptic, the path the sun appears to travel. These signs, Aries, Taurus, Gemini, and so on, are still used today. The 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, were all known to the Babylonians. They called them the wandering stars because they did not follow the fixed patterns of the constellations. Each planet was linked to a god: Jupiter, Marduk; Phanusa, Saturn; Ninurta, Mars; Nergal, Mercury; Nabutha, movements; of these deities across the sky were tracked obsessively. Retrograde motion, the apparent backward movement of a planet, was especially significant and could be seen as a sign of reversal or disruption. From these observations emerged the first true planetary ephemerides charts, predicting where a planet would be on any given day. These were used for both scientific and divinatory purposes. Eclipses fascinated and terrified the Mesopotamians. They noticed that eclipses came in patterns. One of the most important discoveries was the Saros-Sikkala period of approximately 18 years and 11 days, after which solar and lunar eclipses repeat. While the Babylonians may not have understood why eclipses happened, they could often predict them. This is a staggering achievement for such an ancient time. Kings took these predictions seriously. In some cases, they would place a substitute king on the throne during an eclipse, just in case doom befell the royal line. After the danger passed, the substitute would be quietly removed, and the real king restored. The breadth and depth of Babylonian star knowledge were enormous. By 400 BCE, Babylonian astronomers were using arithmetical methods to calculate planetary positions. They plotted curved motion using linear models, developed geometric tools, and even toyed with proto-Algebraic calculations. These weren't mere skywatchers, they were the first mathematical astronomers. Their methods would later influence Greek astronomers like Hipparchus and Ptolemy, and their writings would survive into the Islamic Golden Age, where they were translated and preserved. The Babylonians were not merely preserving the night sky, they were shaping how future civilizations would think about it. Mesopotamian astronomy began with fear and fascination with the sky that spoke in riddles and warnings. But over centuries, it became structured, deliberate, and astonishingly accurate. The same stars that once inspired myths were now measured, named, and charted. The moon's rhythms, once sacred, were now predictable. The planets, once divine agents, were tracked with tables and numbers. A system had emerged, one that balanced science and spirituality, one that looked upward not just in wonder, but with discipline. As we close this chapter, we leave behind a civilization that knew the stars as few ever would. Next, we sail down the Nile to the lands of the pharaohs, where the sun was king and the calendar was born in the floodwaters of the great river. Let the clay tablets rest, let the constellations realign, and let the gentle rhythm of starlight carry you into the next part of our journey. The land of Kemet, the Black Land, unfolds along the twisting ribbon of the Nile. For thousands of years, its people lived by a rhythm deeper than the ticking of clocks. The annual flood, the arc of the sun, the rising of a single bright star that marked the beginning of the year. In Egypt, astronomy was not separate from life. It was life. The movements of the heavens were woven into agriculture, religion, death, and kingship. The very layout of temples and tombs was aligned to the cosmos. To understand the sky in ancient Egypt was to understand time itself. Each summer, the Nile would swell and overflow its banks, bringing fertile silt and fresh water to the fields. This life-giving inundation was the cornerstone of Egyptian prosperity. But what caused the flood? To the Egyptians, the answer lay in the sky. Each year, just before dawn in mid-July, a brilliant star would rise on the eastern horizon's Sopdet, known today as Sirius, the brightest star in the night sky. its heliacal rising, the first appearance. Before sunrise coincided almost exactly with the start of the flood. This was no coincidence to the ancient mind. It was divine timing. The Egyptians celebrated this celestial event with great ceremony. It marked the new year, known as Wepet. Renpet, the opening of the year. It was a moment of renewal, harvest, and cosmic order. Asterisk, while Mesopotamians relied heavily on lunar calendars, the Egyptians pioneered one of the first true solar calendars. By carefully tracking the rising and setting of Sirius and observing the sun's yearly journey, they divided the year into 12 months of 30 days, plus 5 extra days called the Epticamonal, days feast days for the gods. This gave them a total of 365 days, amazingly close to the actual solar year. Though they lacked leap years, this calendar served the Egyptians well for thousands of years, and influenced both the Julian and Gregorian calendars we use today. Time, for the Egyptians, was not linear. It was cyclical, like the stars, like the flood, like life and death. Asterisk, to walk into an Egyptian temple was to walk into the cosmos. Many temples were astronomically aligned, built with extraordinary precision, so that sunlight would enter certain chambers on specific days of the year. At Abu Simbel, the colossal statues of Ramses II sit in a temple, carved from solid rock, twice a year on, or around February 22nd and October 22nd. The sun's rays penetrate the inner sanctuary and illuminate the statues of the gods, including Ramses himself. This was no accident. These days may have marked the king's birthday and coronation, reinforcing his divine link to the cosmos. Similarly, at Karnak, one of the largest temple complexes in the world, long corridors and columns align with solstice points and the sunrise. On sacred festivals, temples were solar machines designed to harness light and shadow, to track time through architecture. In Egyptian cosmology, the sun was not just a light-it, was a god Ra, the solar deity who traveled across the sky in a golden boat each day and through the underworld each night. Each sunrise was his rebirth, each sunset his descent into darkness. This daily cycle mirrored the soul's journey in the afterlife and the eternal pattern of death and renewal. It also inspired daily rituals, royal symbolism, and funeral texts like the Amdwat, which described Ra's night voyage through the underworld's 12 gates. Kings, considered the sons of Ra, aligned themselves with the sun's divine power. Upon death, the pharaoh hoped to join the sun god and rise again, reborn with the morning light. The sky, for Egypt, was not just a place, it was a path. Asterisk, inside royal tombs, particularly in the Valley of the Kings, we find painted ceilings that tell time using decanes, groups of stars that rise sequentially throughout the night. These star clocks divided the night into 12 hours, based on the rising of specific stars. By observing which decan was visible at each hour, priests could track time after sunset with remarkable accuracy. Day and night, time in Egypt was tied to the heavens. Shadow clocks during the day, water clocks and star charts by night. No ticking, no numbers, only sky. Asterisk, in Egyptian tombs, the heavens became maps of eternity. Pyramids were oriented to the north, aiming toward circumpolar stars, those that never set, and were believed to represent immortality. These imperishable stars were where the king's soul would dwell forever, the pyramid texts, among the oldest religious writings in the world, describe the pharaoh ascending like a star, joining the gods in the sky. Later, the Book of the Dead and coffin texts continued this vision, filled with spells and maps to guide the soul among the stars. For the Egyptians, death was not the end. It was a celestial journey. Unlike in Mesopotamia, where astronomy had a strong bureaucratic and civic function, in Egypt it remained closely guarded, deeply ritualistic, and embedded within temple culture. Priests of high ranks, especially those in charge of rituals, were trained in astronomy and mathematics. They used this knowledge to schedule festivals, prepare temples for seasonal ceremonies, and align constructions with celestial bodies. It wasn't astronomy for astronomy's sake. It was cosmic order math, the sacred balance of the universe. The pharaoh ruled not just as a king, but as a maintainer of this balance between sky, earth, and underworld. In Egypt, astronomy was poetry in stone and sunlight. The stars were not just objects, they were gods, signs, destinations, and memories. They guided floods, governed kingship, measured years, opened tombs. The entire civilization, so seemingly focused on eternity, was actually built on celestial cycles. Each brick a measure of time, each ritual a reenactment of cosmic order. As the Nile continues to flow, and the stars continue to rise over the desert, the sky of ancient Egypt remains unchanged, still speaking, still shining, still sacred. As we leave the land of pyramids behind, we head east to a civilization equally ancient, equally wise, China, where skywatching became a tool of imperial legitimacy, weather prediction, and philosophical harmony. Let the temple grow quiet, let the stars drift above the lotus fields, and sleep in the slow rhythm of Sirius, Ra, and the eternal sky. Look eastward to a land of jade mountains, bronze bells, and walled cities, a place where emperors once ruled under a sky that watched and judged all things. In ancient China, astronomy was never just about measuring stars. It was a philosophy, a system of ethics, and a tool of empire to govern the earth. One had to first understand the sky. In Chinese thought, the universe was governed by a grand principle of harmony known as Tianhaven. This was not a place but a force, an order, a presence that permeated all things, and it granted power to rulers under one condition, that they maintain balance and righteousness. On earth, this idea came to be known as the mandate of heaven. If a ruler became unjust, corrupt, or cruel, heaven would respond not through words, but through signs in the sky, comets, eclipses, red suns, sudden storms, or planetary missile, IGNMENTS. In this way, the sky was a mirror of moral order. Astronomers weren't simply scientists, they were guardians of truth, observers of divine judgment. To lose the mandate was to invite rebellion, and many dynasties fell by signs read in the stars. As early as the Zhou dynasty c. 1046 BCE, Chinese rulers employed court astronomers whose sole job was to monitor celestial changes. These men were often eunuchs or officials, trained not just in mathematics but in Confucian, ethics, and Taoist philosophy. They worked in astronomical bureaus, specially constructed observatories, where they recorded eclipses, tracked planets, and aligned calendars. One of the earliest known observatories is a set of stone pillars at Dengfeng, built in the Western Zhou period, aligned with the solstices to measure the solar shadow and track time. Later dynasties, particularly the Han and Tang, built elaborate observatories with bronze armillary spheres, water clocks, and sighting tubes to enhance precision. These instruments weren't just for curiosity, they were instruments of state. The Chinese developed one of the most complex and enduring calendrical systems in the world. It was a lunisolar calendar, blending both the solar year and lunar month. 12 months of 29 or 30 days made a year. But to keep pace with the solar cycle, leap months were added in a 19-year cycle. Each year was also paired with a heavenly stem and earthly branch, creating a 60-year cycle used to track time, personalities, and fates. The calendar was not just practical, it was sacred. Only the emperor could issue a new calendar. It was his celestial signature, proof that he ruled in harmony with the cosmos. Unlike the 12 Western zodiac signs, the Chinese sky was divided into 283 star groups called Zhu, or lunar mansions. The most important constellations were grouped into the 4 symbols, each associated with a direction, a season, and a creature: azure dragon of the east, spring vermilion; bird of the south, summer; white tiger of the west, autumn; black tortoise of the north, winter. At the very center of the sky was the purple forbidden enclosure, a celestial palace surrounding the North Star, symbolic of the emperor's own position at the center of earthly order. This heavenly map was reflected in the layout of palaces, cities, and even tombs. The sky was Earth's pattern. To live rightly meant to live in accordance with it. In Chinese records, solar and lunar eclipses were often seen as omens of great change. One of the earliest recorded eclipses appears in the Book of Documents from around 2137 BCE, according to legend. 2 court astronomers, Shi and Ho, failed to predict an eclipse and were executed for their negligence. Whether true or myth, the story reflects the seriousness of skywatching in royal courts. Eclipses were often accompanied by political unrest or natural disasters. If an emperor's reign grew corrupt, heaven would obscure the sun to signal its disapproval. This connection between cosmic irregularities and political legitimacy made accurate astronomy both powerful and dangerous. The Chinese kept meticulous records of unusual sky phenomena more than any other ancient civilization. Over 2,000 years of observations describe comets, meteors, sunspots, and auroras. They called comets broomstars, believing they swept misfortune across the sky. Their tails pointed to areas where disaster might strike: plague, rebellion, or war. Because of this belief, court astronomers had to interpret such sightings delicately. A misread comet could spark panic or give political opponents ammunition to challenge the throne. By the Han Dynasty 202 BCA, 226, Chinese astronomy had become increasingly mathematical. Scholars like Zhang Heng developed rotating armillary spheres to model the heavens. Water clocks measured time with remarkable consistency, often accurate to the minute. In later centuries, astronomers like Guo Shujing would build tall shadow-casting poles to measure the Earth's curvature and develop calendars accurate to within seconds of the modern year. Even during the Ming and Qing dynasties, Chinese astronomers worked alongside Jesuit missionaries to refine planetary models and improve precision. But all of it, every calculation, every model was still rooted in the idea that heaven and earth must stay aligned. Science served balance. Knowledge served harmony. Many Chinese astronomical records are so detailed that modern scientists use them to verify historical events. Descriptions of Halley's Comet, solar eclipses, and meteor showers allow researchers to date events with extraordinary accuracy. Some Chinese star maps, such as the one found in the Dunhuang Caves, are so precise that they remain useful even today. This uninterrupted chain of observation, spanning more than 3,000 years, is among the longest in human history. In China, the stars were more than stars. They were principles, patterns, warnings, blessings. They told of dynasties rising and falling, of floods and droughts, of justice and ruin. The emperor looked upward, not to wonder, but to answer. And so, each night, court astronomers stepped into the cold, opened their scrolls, and peered at the heavens, not for themselves, but for the nation. Let the palace walls grow silent, let the brushstrokes dry, and let the soft glow of starlight drift across the forbidden city. Next, we cross the great mountains westward into a world of epic poetry and logical stars, the Greek world, where philosophy and astronomy would intertwine like constellations. In a dark sky. Sleep now, under the quiet sky of the Middle Kingdom. The ancient Greeks did not simply watch the stars, they interrogated them. To Greek thinkers, the heavens were not just divine, they were orderly, measurable, and rational. Every light in the sky, every motion of a planet, every eclipse or seasonal change, these weren't omens from gods, but clues to a deeper, elegant truth. Their quest was not just to observe the universe, but to understand its underlying structure, and in doing so, they laid the foundations of modern astronomy. Greek skywatching began, like elsewhere in myth. Constellations such as Orion, Andromeda, and Cassiopeia were seen as divine stories etched into the stars. But as Greek philosophy blossomed in the 6th century BCE, thinkers began turning myth into inquiry. In Miletus, a city on the western coast of Anatolia, proposed that the universe was governed not by capricious gods, but by natural laws. He is credited with predicting a solar eclipse in 585 BCE, an astounding feat, even if partially apocryphal. Others followed. Anaximander suggested that Earth floated freely in space. Anaximenes proposed the sky was made of air, thin and stretched. Heraclitus claimed the cosmos was in constant flux, like fire. These early philosophers didn't get everything right, but they asked new kinds of questions, which would change the course of history. One of the most important breakthroughs in Greek astronomy was the belief that Earth was a sphere. Pythagoras, best known for his theorem, may have been the first to argue for a round Earth around 500 BCE. Based on the shape of the moon and the curved shadow seen during lunar eclipses later. Aristotle 384 to 322 BCE presented three main arguments for Earth's sphericity. Ships disappear bottom first over the horizon. Travelers going south see new constellations. The Earth casts a round shadow on the moon during eclipses. These observations showed that logic and geometry could describe the cosmos perhaps better than myth ever had. Greek astronomy entered a golden age with thinkers who combined mathematics, observation, and mechanical models. Eudoxus of Cnidus c. 4th century BCE, he proposed a model where the planets moved in nested spheres, each turning at a different rate. It was the first geometric model of the cosmos, though it couldn't account for all observed planetary motions. Aristarchus of Samos, perhaps the most revolutionary of all. Around 270 BCE, Aristarchus proposed a heliocentric model placing the Sun at the center, not Earth. His idea would be ignored for nearly 1,800 years until revived by Copernicus. He also attempted to calculate the distance to the Moon and Sun, using angles of light during lunar eclipses. Though his numbers were off, his method was remarkably sound. Eratosthenes in one of the most elegant achievements in all of ancient science. Eratosthenes, 276 to 194 BCE, measured the circumference of the Earth using shadows cast at different cities at noon. His result, about 39,000 kilometers, amazingly close to the actual value. The Greeks believed the heavens were arranged in perfect spheres, rotating in uniform circular motion. This idea came from Plato, who believed that the most divine motion was the circle, endless, smooth, eternal. But planetary motion was anything but smooth. Planets wandered. Sometimes they even appeared to move backward, a puzzling behavior called retrograde motion. To explain this, Hipparchus c. 190 to 120 BCE, a brilliant observer and mathematician, introduced the idea of epicycles, small circular orbits riding atop larger ones. Though it complicated the idea of perfect circles, it helped make predictions far more accurate. Hipparchus also compiled one of the first comprehensive star catalogs, listing over 800 stars by brightness and position. Discovered the precession of the equinoxes, the slow wobble of Earth's axis over centuries. He was a true bridge between observation and theory. The culmination of Greek astronomy came in the 2nd century CE with Claudius Ptolemy, whose work Almagest would dominate astronomy for over 1,400 years. Ptolemy synthesized centuries of Greek thought, formalized the geocentric model, placing Earth at the center, with planets orbiting in complex epicycles. Introduced concepts like eccentrics and equants to explain irregular motion, though we now know his model was incorrect. It was a powerful predictive tool, one that let astronomers chart eclipses, planetary conjunctions, and lunar phases with great accuracy. It was not the truth of the cosmos, but it was close enough for centuries. What set Greek astronomy apart was not just its accuracy, it was its spirit. Philosophers debated the purpose of the heavens. Were the stars eternal and divine, or were they distant suns? Did celestial harmony mirror moral or aesthetic perfection? Plato saw the cosmos as a living being. Aristotle viewed it as a set of interlocking causes. The Stoics believed that celestial order reflected rational fate. To study the heavens was to study truth, beauty, and ethics all at once. Instruments and observations. The Greeks developed early tools to aid in observation. Astrolabes used to measure the altitude of stars and planets. Armillary spheres, metal rings showing celestial circles. Gnomons, vertical sticks or obelisks, to track shadows and solar time. They observed eclipses, solstices, planetary cycles and recorded them with precision and reverence. And yet, They still saw the sky as divine, even in their logic. There was wonder. The Greeks handed the world something unique, the belief that the sky could be explained, not just worshipped. They mapped stars not as gods, but as objects in a system. They asked why, and then proved how. Their errors were many, but their tools, ideas, and methods shaped the very birth of science, as the Roman Empire absorbed the Greek world. Many of these ideas were preserved, but it would be in another great civilization, the Islamic Golden Age, that Greek astronomy would be revised, corrected, and expanded with dazzling brilliance. Let the stars wheel overhead. Let the scrolls rest in stone libraries, and drift gently through the quiet geometry of the night sky. As the Western Roman Empire faded into decline, much of classical knowledge teetered on the edge of disappearance. But in the East, from the deserts of Persia to the courts of Baghdad and the cities of Al-Andalus, brilliant flame was kindling. This was the Islamic Golden Age, a period from the 8th to the 14th century, when science, philosophy, and art flourished across the Muslim world. Here, ancient Greek, Indian, and Persian astronomical texts were translated, corrected, and expanded, often by polymaths, who were poets and engineers, philosophers and doctors, all in one, under the vast night skies of the Islamic world. Astronomy became a global endeavor. Islam places deep emphasis on the observation of nature, and the heavens held special significance. The Quran contains numerous verses that speak of the stars as signs, the moon as a measure of time, and the sun as a servant of divine order. Faith and observation were not at odds, they were harmonious. Astronomy was essential to determining prayer times, which shift daily based on the sun's position. Finding the Qibla, the direction of Mecca, for daily prayers. Calculating the lunar Islamic calendar, used to mark months like Ramadan. Predicting eclipses, equinoxes, and solstices, for agricultural and religious purposes. In this context, rulers funded observatories. Scholars pursued the sky not only for curiosity but to fulfill spiritual, mathematical, and practical needs. In the 9th century, the Abbasid Caliphate established the Beit al-Hikmah, the House of Wisdom in Baghdad. This became the most important intellectual center of the early Islamic world. Greek works by Ptolemy, Aristotle, and others were translated into Arabic, often with extensive commentaries. Indian works like the Siddhantas and Persian texts were also studied. From this confluence emerged a new synthesis of astronomy, one that kept ancient knowledge alive while surpassing it. Among the most famous scholars was Muhammad ibn Musa al-Khwarizmi, c. 780–850, whose name gave us the word algorithm. He wrote one of the earliest Islamic Ziggurat set of astronomical tables filled with data on planetary motions, eclipse calculations, and celestial coordinates. His Ziggurat Al-Sintind, based on Indian and Persian sources, marked the beginning of a uniquely Islamic astronomical tradition. These Zigguras were not just scientific texts. They were tools used by astronomers across the Muslim world and eventually into Christian Europe. Islamic astronomers refined and developed a wide array of astronomical instruments, many of which would later be used in the Renaissance. Perfected in the Islamic world, these beautiful brass devices allowed users to determine the time, latitude, and position of stars with incredible accuracy. Armillary spheres, used to model celestial movements. Quadrants and sextants, large-scale instruments, used in observatories to measure the angle of celestial bodies. Some astrolabes were inscribed with Qibla-finding grids, helping travelers determine prayer direction no matter where they were on Earth. These instruments were both scientific tools and works of art, engraved, calibrated, and often passed down across generations. Many Islamic rulers built state-funded observatories, places dedicated to night-long observations and mathematical study. Maraga Observatory, Iran, 13th century, founded by Nasir al-Din al-Tusi. It was equipped with massive instruments and employed dozens of scholars. Al-Tusi devised a model known as the Tusi couple, which allowed circular motions to produce linear motion, an innovation that would later influence Copernicus. Ola Beg Observatory, Samarkand, 15th century, built by the Timurid Prince Ola Beg. This observatory featured a massive sextant, over 50 meters in radius. Ula Beg compiled a star catalog listing over 1,000 stars, surpassing Ptolemy's in precision. These observatories weren't just buildings, they were temples of reason, where scholars stood under the stars and rewrote the sky with numbers. While Ptolemy's Almagest was revered, Islamic astronomers were not afraid to challenge him. Al-Battani, 858 to 929, corrected Ptolemy's values for the length of the year and the precession of the equinoxes with greater accuracy. Ibn al-Shatir, 1304 to 1375, a Damascene astronomer, proposed models for the moon and planets that eliminated the equenta key flaw in Ptolemy's system. His ideas would later be mirrored, almost exactly, by Copernicus. Instead of passive preservation, Islamic scholars tested inherited models. They ran observations over centuries. When the data didn't fit, they refined it. Their work kept astronomy dynamic, empirical, and alive. Astronomical tools were also vital for the flourishing of Islamic navigation. Mariners used astrolabes to determine latitude while at sea. Star charts guided them through the Indian Ocean, Arabian Sea, and Mediterranean. Mathematical models helped predict eclipses and tides, essential for port entries and coastal voyages. In this way, Islamic astronomy fed into the global age of exploration, centuries before European navigators set sail across the Atlantic. Islamic astronomy was not confined to the Arab world. In Al-Andalus, Muslim Spain, scholars like Azarqali Arzachil developed universal astrolabes and advanced solar theories on North Africa, Sub-Saharan Africa, Persia, and Central Asia. Astronomy flourished in local dialects, cultural practices, and religious traditions, and through translations into Latin, especially by scholars in Toledo and Sicily. These texts flowed into medieval Europe, sparking the first flickers of the Renaissance. The Islamic Golden Age did something extraordinary. It saved the stars. While Europe slept, 1,000 candles burned in Baghdad, Cairo, Samarkand, and Cordoba, recording, refining, and imagining the sky. The scholars of this age did not just honor the cosmos. They challenged it, modeled it, and improved its image. They were bridge builders, linking ancient Babylon to future Florence, Ptolemy to Galileo. Myth to math. As we close this chapter, the sky still spins, the stars still move, and their names, Betelgeuse, Aldebaran, still carry the echoes of Arabic voices. Let the observatories dim, let the ink dry on parchment, and rest beneath the measured sky of reason and revelation. By the early Middle Ages, much of Europe had lost direct access to classical science. After the fall of the Western Roman Empire, centuries passed in which astronomy faded into the background, preserved mostly in fragments by monks and scholars within religious institutions, but the stars never disappeared, and by the 12th century, Europe would begin to rediscover the sky thanks largely to translations from Arabic, encounters with the Islamic world, and a rising interest in learning driven by cathedrals, universities, and monastic scholarship. In the early medieval period, roughly 500 to 1000 CE, astronomy survived in Christian Europe primarily through monastic learning. Monks observed the heavens to regulate liturgical calendars such as Easter's date, prayer times based on sunrise and sunset, agricultural planning through solstices and equinoxes. Texts like Isidore of Seville's Etymologia and the Computus manuals offered basic explanations of celestial phenomena. However, these were conceptual summaries, often mixing theology with fragments of older Roman knowledge. They were not observational sciences, but they kept the vocabulary of the sky alive. The real rebirth began in the 12th century, with the translation movement, centered in places like Toledo, Spain, where scholars translated Arabic texts into Latin, Palermo, Sicily, where Greek, Latin, Arabic, and Hebrew knowledge coexisted. Monte Cassino and Cluny, major monastic centers for script preservation. Dozens of key works came into full European hands for the first time in centuries. Ptolemy's Almagest, an Arabic translation, Al-Zarqali's astronomical tables, treatises on the astrolabe and planetary motion. These translations reintroduced trigonometry, spherical geometry, and accurate star tables into Europe, fueling a new phase of sky study. In medieval universities, the study of astronomy was considered one of the four mathematical arts, alongside arithmetic, geometry, and music. These four formed the quadrivium, which followed the trivium: grammar, logic, rhetoric. Astronomy wasn't studied for curiosity alone, it was seen as a path to divine truth. The heavens were ordered, and that order reflected the mind of God. Thus, studying planetary cycles, eclipses, and star movements was part of the broader theological and philosophical education. The geocentric model of Ptolemy, with Earth at the center and the stars fixed in a crystal sphere, fit neatly into medieval Christian cosmology. Heaven was above, hell was below. Earth, imperfect and changing, lay at the center of it all. This model was expanded in theological texts, most notably by Thomas Aquinas, who harmonized Aristotle with Christian doctrine. In his view, the outer spheres were moved by divine intelligences, movers giving purpose to the cosmos, though not scientific by modern standards. This worldview was deeply coherent, a fusion of observation, philosophy, and faith. One of the most important astronomical tools of medieval Europe was the astrolabe. Reintroduced via Arabic treatises, it allowed scholars to measure the altitude of celestial bodies, determine time and latitude, solve complex trigonometric problems, predict sunrises, moon phases, and prayer times. By the 14th century, were common in universities and royal courts, crafted from brass, beautifully engraved, and passed from scholar to scholar. They symbolized the return of precision to European astronomy. In the 13th century, King Alfonso X of Castile, known as Alfonso the Wise, sponsored a group of scholars to revise and improve existing Arabic star tables. The resulting Alphonsine tables, completed around 1252, allowed astronomers to calculate the positions of the Sun, Moon, and planets with new precision. They became standard across Europe until the 16th century. These tables were not based on new physics, but they represented a serious commitment to observation, data, and revision. By the 13th century, universities in Oxford, Paris, and Bologna had become centers for astronomical study. Scholars such as Robert Grosseteste, Roger Bacon, Nicole Aurel began applying logic and early empirical methods to celestial phenomena. They explored topics like the nature of planetary motion, the possible rotation of Earth, atmospheric optics, rainbows, halos, timekeeping, and mechanical clocks, while still operating within a Ptolemaic framework. Their work planted seeds for the revolutions to come. In medieval Europe, the sky wasn't just studied in text, it was carved in stone. Cathedrals such as Chartres, Amiens, and Strasbourg were built with astronomical alignments in mind. Windows, rose patterns, and sunlit arches tracked solstices and equinoxes, liturgical feast days, noon and sunset points. These buildings were stone calendars, expressing the belief that sacred time and celestial time were one. In this age, stars were also woven into literature and spiritual vision. In Dante Alighieri's Divine Comedy, each realm of the afterlife is guided by celestial order. The stars crown heaven. Planetary spheres mark the journey of the soul. God himself is the love that moves the sun and the other stars. Astronomy was both science and poetry, both math and metaphor. By the late 14th and 15th centuries, a quiet momentum had built. Across Europe, accurate planetary tables were in use. Universities taught spherical astronomy regularly. Artists and builders understood solar angles and seasonal cycles. Scholars like Regiomontanus and Georg Purbach had begun simplifying and correcting Ptolemaic models. The stars were no longer distant. They had become measured, questioned, and readied for a transformation. And soon, in the hands of a man from Poland, Nicolaus Copernicus, the entire universe would turn. Let the bells of the monastery fall silent. Let the astrolabe rest on the shelf. And let the quiet sky of Europe whisper one final truth. The stars are waiting to move again. By the dawn of the 16th century, Europe stood at a threshold. The sky, so long believed fixed and eternal, was beginning to shift ever so slightly in the minds of the learned. Whispers of error had crept into the old Ptolemaic model. Planetary tables were misaligned. Eclipses arrived off schedule. The stars, so orderly in theory, seemed less cooperative in practice. Something, it seemed, was wrong with the heavens. Then came a quiet scholar from Poland, a canon of the church, a man who doubted the stillness of earth. His name was Nicolaus Copernicus, and he would move the world in 1543. The year of his death, Copernicus published his life's work, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. In it, he proposed something astonishing, that the earth revolved around the sun. This heliocentric model placed the Sun at the center, with Earth and the other planets orbiting it. The Moon still orbited Earth. The stars were infinitely far away. For Copernicus, the new system explained several problems. Retrograde motion, the strange backwards movement of planets, was no longer a mystery. It was simply the result of Earth overtaking slower planets in its orbit. The seasons, equinoxes, and the precession of the equinoxes made more sense. A rotating Earth explained the daily rising and setting of stars without needing the entire cosmos to spin. Yet Copernicus kept his ideas mathematically dense and philosophically cautious. He retained circular orbits and epicycles, afraid of challenging the full weight of tradition. Still, his sun-centered model planted a seed that would reshape the sky forever. More than half a century later, that seed would bloom under the watchful eye of a man with a telescope. In 1609, Galileo Galilei, an Italian physicist and astronomer, turned a recently invented device, the telescope, toward the sky. What he saw shocked the world. Mountains and craters on the Moon, showing it was not a perfect sphere. Moons orbiting Jupiter, 4 little dots moving around a planet, proving not everything revolved around Earth. Phases of Venus impossible to explain in a geocentric model. Sunspots, dark blemishes moving across the Sun, showing that even it was not unchanging. These were visual, undeniable proofs that the old Aristotelian cosmos was flawed. Galileo published his findings in 1610 in Sidereus Nuncius's Starry Messenger, dedicating it to the Medici family, who became his patrons. The universe was no longer perfect. It was scarred, dynamic, and filled with motion. Galileo didn't stop at observation. He argued for Copernicanism openly, with wit and sharp reasoning. In 1632, he published Dialogue concerning the two chief world systems, which compared the Ptolemaic and Copernican models through a fictional debate. Though Galileo claimed neutrality, the character defending geocentrism was named Simplicio, the simpleton, a choice that did not go unnoticed. The Church responded swiftly. In 1633, Galileo was summoned before the Roman Inquisition. Forced to recant under threat, he spent the rest of his life under house arrest. Yet his ideas spread, unstoppable. His telescope had opened the heavens, and no amount of silence could close them again. At the same time, Galileo was peering through glass. A German mathematician named Johannes Kepler was poring over star tables and discovering something even more radical. Working with data collected by Tycho Brahe, a Danish nobleman who had recorded planetary positions with extraordinary accuracy, Kepler found that planetary orbits were not circles, but ellipses. From this, he derived 3 laws of planetary motion. Elliptical orbits. Planets orbit the Sun in ellipses, with the Sun at one focus. Equal areas. Planets sweep out equal areas in equal times, meaning they move faster when closer to the Sun. Harmonic law. The square of a planet's orbital period is proportional to the cube of its distance from the Sun. These laws demolished the need for epicycles, equants, and crystalline spheres. They offered, for the first time, a mathematically correct map of the solar system. The implications of these discoveries were profound. Earth was no longer the center of the universe. The heavens were not perfect or immutable. The laws of motion applied universally to both sky and earth. Nature was predictable, rational, and mathematical. The cosmos became mechanical, yet beautiful. a great clockwork driven not by divine perfection but by natural laws, understandable by reason. And though the Church resisted for a time, eventually even it would come to accept the heliocentric model. The stage was now set. Copernicus had shifted the center, Galileo had revealed the imperfections. Kepler had found the paths. What remained was to explain why the planets moved as they did. That answer would come in the next century, from a quiet Englishman with an apple and a question. Let the moons of Jupiter drift in silence. Let the telescope cool in the night air. Let the earth turn gently beneath your feet. The stars are no longer fixed. The earth is no longer still. And the universe has begun to speak in the language of laws. It is the year 1687. Europe is changing. The telescope has reshaped the eye. Mathematics has reshaped the mind. And the sky, once filled with gods and omens, has become a realm of questions calm, orderly, and full of silent motion. Into this world steps Isaac Newton, a quiet, intense man from Lincolnshire, whose thoughts reached farther than the stars. With one book, he would bind together centuries of thought from Babylon to Brahe, from Aristotle to Galileo, and give the world its first true model of the universe as a system in 1687. Newton published his most famous work, Philosophiae Naturalis Principia, Mathematicon, known simply as the Principia. It contained three revolutionary ideas: law of inertia, an object in motion stays in motion, and an object at rest stays at rest unless acted upon by a force. F equals ma, force equals mass times acceleration, a mathematical way to describe how and why things move. Action-reaction. For every action, there is an equal and opposite reaction. These laws applied to apples falling from trees, carriages rolling across cobblestones, and most astonishingly to the heavens themselves. Newton proposed that every object in the universe attracts every other object with a force that increases with mass, decreases with distance, always pulls not pushes. Was the law of universal gravitation. It explained why apples fall, why the moon orbits the earth, why the planets curve around the sun. It gave reason to the tides, the shape of Earth's orbit, the path of comets. For the first time in history, a single law described both the motion of the stars and the objects on Earth. Newton's cosmos was one of precision, a clockwork mechanism, powered by force, guided by number, and written in the language of calculus field. Newton helped invent everything could be measured, predicted, calculated. There were no more celestial spheres, no more epicycles numbered, more need for special physics in the heavens. Earth and sky were governed by the same rules. This gave rise to a new vision of the universe, the mechanical cosmos. Like a vast, intricate clock, the heavens ticked forward. Each planet moved along its path with mathematical inevitability. The stars obeyed laws, not mysteries. The divine was not absent, but it was now the architect, not the daily mover. God had set the universe in motion, and now it ran on its own. This was a cosmic revolution unlike any before, not one of mystery, but of certainty. Newton's laws matched reality. Halley's comet, returning as predicted, confirmed gravitational paths. Lunar and solar eclipses were predicted with accuracy. Tides were explained by the moon's pull. The bulge at Earth's equator was measured and confirmed, just as Newton said, across Europe. Scientists used his laws to chart new stars, calculate planetary orbits, and build the first accurate star maps. The Royal Society and academies across France, Germany, and Italy embraced Newton's work. The scientific revolution was no longer just an idea, was a method. Newton was not alone. He stood on the shoulders of giants and, alongside brilliant minds, Edmund Halley promoted Newton's work and confirmed the path of comets. Leibniz, in Germany, helped develop calculus independently. Flamsteed and Cassini mapped the stars with unprecedented accuracy. Christian Huygens refined optics and discovered Saturn's rings. Together, they created a world where the sky was not only beautiful, but understandable. Newton's approach: observation, hypothesis, mathematics, verification, became the foundation of modern science. His tools were measurement, experiment, calculation, peer review. This spirit extended far beyond astronomy, touching chemistry, physics, engineering, and biology. It changed not just how we studied the universe, but how we understood truth itself. And yet, even as Newton revealed the workings of the heavens, something subtle was lost. The stars were no longer mysterious or divine. They were now points of mass, obeying formulas. The sky had become a system, predictable, mechanized, finite, but in this clarity, there was a new kind of wonder, a deeper, quieter. An apple had fallen, a thought had formed, and now the cosmos moved to the music of math with Newton. The long journey from myth to model was complete. The Mesopotamians had charted the stars. The Egyptians had timed the floods. The Greeks had modeled the heavens. The Islamic scholars had refined the numbers. The medievals had preserved and passed them on. The Renaissance had questioned everything. Asterisk and Newton had pulled it all together with one idea, that everything moves, and that motion can be understood. Let the pendulums swing. Let the comets return. Let the sun rise not because it must, but because it is written in the laws of motion. Sleep now, in a universe that no longer hides its patterns. The sky is no longer chaos. It is code. Asterisk, the 18th century dawned under the firm light of reason. With Newton's laws in place and telescopes improving, Europe entered the Age of Enlightenment, a period of intellectual transformation that prized observation, classification, and skeptical inquiry. The heavens were no longer sacred mysteries, they were phenomena to be studied, catalogued, and explained. But the more astronomers looked, the more the sky seemed to expand beyond comprehension. In Paris, London, Berlin, and St. Petersburg, state-funded observatories began rising across Europe. These were no longer solitary monks with astrolabes. These were teams of trained astronomers using precise clocks, finely ground lenses, and well-funded programs to record the heavens night after night. Some of the great centers included Greenwich Observatory, England, established for navigational accuracy; Paris Observatory, France, a hub of scientific debate and celestial mechanics; Berlin Observatory, home to meticulous sky mapping; Royal Swedish Academy of Sciences, which promoted planetary and lunar observations. Kings and queens now supported astronomy not for poetry, but for navigation, mapping, and empire. The telescope, refined through the 17th and 18th centuries, grew ever more powerful. Larger mirrors, better optics, and darker observing conditions allowed astronomers to peer deeper into space than ever before, and with each improvement, The number of visible stars, nebulae, and double systems increased. No longer was the sky a collection of wandering planets and fixed stars. It was a dynamic population, layered, distant, and crowded with structure. In the late 1700s, a German-born musician turned astronomer named William Herschel became one of the most prolific skywatchers of all time, with the help of his sister, Caroline Herschel. He discovered Uranus in 1781, the first new planet in modern history, built some of the largest telescopes of his day, cataloged over 2,500 deep sky objects, nebulae, star clusters, and galaxies. Noticed that the Milky Way was not a sphere but a flattened disk. Herschel even speculated that the stars were distributed in layers, and that we lived inside a galactic system, perhaps surrounded by many others. Though his understanding was limited by technology, his ambition was enormous. He once said, "The heavens are a vast laboratory of time." Astronomy became practically indispensable to global exploration. Using star positions and lunar observations, sailors could calculate their longitude at sea, a crucial factor in avoiding shipwrecks and reaching distant lands accurately. Marine chronometers, like those developed by John Harrison, allowed sailors to carry accurate time across oceans. The Nautical Almanac, first published in 1767, gave tables of moon positions for navigation. Astronomy was no longer just a scientific curiosity, it was a tool of empire. Even as astronomers charted positions, a new question began to take shape. What are stars made of? In the Enlightenment era, scientists began studying the nature of light. Isaac Newton had shown that white light splits into a rainbow spectrum. Others discovered interference patterns, refraction, and color mixing. But it would be in the next century, through spectroscopy, that light would become a tool for reading stellar composition. For now, though the stars remained silent points of light, beautiful, mysterious, and countless, as more stars and nebulae were discovered, astronomers began asking, how far away are they? Is the Milky Way the whole universe or just a part of it? Are nebulae clouds of gas or distant star systems? Answers remained out of reach. Without a way to measure stellar distances, even the nearest stars seemed impossibly far. But something had changed. The concept of the universe had grown. What was once a neat set of nested spheres was now a hazy immensitian ocean of unknowns, stretching far beyond what any model could capture. The Enlightenment also brought astronomy into the salons, coffee houses, and public lectures of Europe. Educated citizens owned celestial globes and planetarium charts. Pamphlets and periodicals described new comets, eclipses, and lunar phenomena. Poets and painters turned to the stars for inspiration. Astronomy became a kind of shared dream uniting science, art, and philosophy. And as the industrial age approached, a new generation of astronomers would soon do what seemed impossible. They would measure the distances to stars. They would discover that the Milky Way was not alone, and they would find, hidden in the faintest light, the story of the entire universe's birth. But for now, let the great telescopes rest. Let the almanacs close. Let the candles of reason flicker gently beneath a sky just beginning to open. The cosmos is vast, but it is not beyond knowing. The Enlightenment had mapped the heavens, but still, the stars were out of reach. No one knew how far they were. No one could prove whether nebulae were nearby clouds or distant galaxies. What came next was not a revolution of philosophy, but of precision instruments, photographic plates, and spectral lines. The 19th century was the age when astronomy became astrophysics. One of the oldest questions in astronomy, how far away are the stars, was finally answered using an ancient technique called parallax. Parallax is the slight shift in a star's position when observed from different points in Earth's orbits 6 months apart. It had been suspected since the Greeks, but the shift was too small to detect with earlier instruments. Then, in 1838, German astronomer Friedrich Bessel measured the parallax of 61 Cygni, a faint double star. His result, over 10 light-years away, an almost incomprehensible distance, more than 60 trillion miles. Suddenly, the sky grew enormous. Other astronomers followed. Wilhelm Struve measured Vega. Thomas Henderson calculated the distance to Alpha Centauri. Each new measurement confirmed the stars were not just points. They were worlds, shining from light-years away. In the mid-1800s, photography began to transform how the heavens were studied. In 1840, John William Draper took the first detailed photo of the moon through a telescope. In 1850, the first daguerreotype of a star Vega was captured at Harvard Observatory. By the 1880s, long-exposure photography revealed thousands of faint stars invisible to the eye. With photographic plates, astronomers could record the sky permanently, compare changes over time, spot new stars, novae, and moving objects, catalog entire regions of the Milky Way. The sky was no longer fleeting. It had become archivable. A second revolution came with spectroscopy, the study of how light splits into its component colors. In the 1850s and 60s, scientists like Gustav Kirchhoff, Robert Bunsen, Joseph Fraunhofer discovered that every element leaves a unique signature in the light it emits or absorbs. This meant that by passing starlight through a prism, astronomers could determine what stars were made of, their temperature, their motion toward or away from Earth, whether they were single stars or binary systems. It was an astonishing breakthrough. For the first time, humans could know that the same elements on Earth, hydrogen, helium, iron, exist in stars trillions of miles away. The universe was not foreign, it was familiar. With better star counts and photographic maps, astronomers now tackled an even larger question: what is the shape of our galaxy? Using star density, extinction, the dimming of starlight by dust, and statistical models, astronomers like Jacobus, Captain William Herschel, earlier Edward Pickering, and his team at Harvard began to sketch a flattened, disk-like Milky Way, filled with stars and gas. They proposed that the sun was not at the center, but slightly off to one side, marking a quiet shift in our cosmic ego. Though limited by available tools, these efforts were the first drafts of galactic cartography at Harvard College Observatory. A group of women known as computers worked under director Edward Pickering to analyze stellar spectra from thousands of photographic plates. These women, many of them overlooked in their time, made lasting contributions. Annie Jump Cannon developed the spectral classification system still in use today, OBAFGKM. Henrietta Swan Leavitt discovered a relationship between the brightness and pulsation of Cepheid variable stars, a breakthrough that would later allow astronomers to measure intergalactic distances. Williamina Fleming catalogued hundreds of novae, binary stars, and stellar spectra. Their work was foundational, laying the groundwork for 20th century astrophysics. Thanks to spectroscopy, astronomers discovered that stars are hot balls of gas, primarily hydrogen and helium. Their colors reflect their surface temperatures, from cool red stars to blazing blue giants. Many stars exist in binary or multi-star systems, orbiting common centers of mass, and perhaps most astonishing, the Sun, so central to life on Earth, is just another average star. The stars were not alien, they were our cosmic siblings. The 19th century also saw progress closer to home. New moons were discovered orbiting Jupiter, Saturn, and Uranus. Asteroids were identified between Mars and Jupiter, tiny worlds filling the space where a planet might have been. Neptune was predicted mathematically and discovered in 1846. Based on irregularities in Uranus's orbit. It was a time of sky mapping, of cataloging, of discovery upon discovery. Finally, the 19th century brought questions of time into focus. Geologists, like Charles Lyell and James Hutton, showed that Earth's features formed slowly over millions of years. And in astronomy, there were hints that stars evolve, change brightness, and eventually die. The stars were no longer eternal, they had lifespans. The universe was not just large, it was old. By the end of the 1800s, astronomy had become a data science. Precise star charts, vast photographic archives, spectral catalogs, celestial mechanics, telescopes of increasing power, and, just over the horizon, in the 20th century, would come Einstein's theory of relativity, Hubble's discovery of galaxies beyond the Milky Way, the realization that the universe is expanding. But here, in the quiet sky of the 19th century, a truth had taken hold. The stars were no longer unreachable. They were distant but measurable, burning but knowable, ancient but made of the same matter as ourselves. Let the telescopes stand still. Let the plates rest in their wooden drawers. Let the women of Harvard pause their calculations. The universe is waiting to speak again in deeper light, over vaster distances, and soon it will asterisk. As the 1800s faded, the stars had been measured, photographed, and catalogued. The Milky Way was known to be vast, but most still believed it was the entire universe. Then came the 20th century, and with it, a flood of discoveries that would redefine space, time, and everything between. In 1915, Albert Einstein published his general theory of relativity, which described gravity not as a force, but as the warping of space-time by mass and energy. This elegant theory replaced Newton's invisible pull with a new vision. Massive objects like stars and planets bend the space around them. Light itself follows these curves. Time flows slower near stronger gravity. The universe is not fixed, it can stretch, curve, and change shape. Einstein's equations were so powerful, they predicted the expansion of the universe. But Einstein himself didn't believe it. He introduced a cosmological constant to keep the universe static. He would later call this his greatest mistake. In the 1920s, astronomer Edwin Hubble, using the Hooker telescope on Mount Wilson in California, made two monumental discoveries. 1. The universe is bigger than the Milky Way by measuring Cepheid variable stars using Henrietta Leavitt's method. Hubble showed that the Andromeda Nebula was not within our galaxy, it was an entire galaxy of its own, millions of light-years away, Suddenly, the Milky Way became just one of billions of galaxies. The universe was not only large, it was enormous. 2 galaxies are moving away from us next. Hubble and colleague Milton Humason measured the redshift of light from distant galaxies, how their light was stretched toward longer, redder wavelengths. This shift showed that galaxies were receding the farther away they were, the faster they moved. The conclusion was revolutionary. The universe is expanding. This matched Einstein's original equations and confirmed a new model of the cosmos, one that had a beginning. In the 1930s, Belgian priest and physicist Georges Lemaitre proposed what he called the primeval atom, an initial point from which the universe expanded. This idea became known as the Big Bang theory, that the universe had once been infinitely small, hot, and dense and had been expanding ever since. At first, the idea was controversial. Some preferred the steady-state model, in which the universe had no beginning or end, just continuous expansion and matter creation. But evidence kept building for the Big Bang. The most powerful confirmation came by accident. In 1964, radio engineers Arno Penzias and Robert Wilson were trying to reduce noise in their antenna. But no matter what they did, a faint background hiss remained coming equally from every direction in space. They had stumbled upon the cosmic microwave background radiation, the afterglow of the Big Bang itself still echoing through the cosmos. Billions of years later, this light, now stretched into microwaves, is the oldest thing we can see, a silent map of the infant universe. The Big Bang model explains the abundance of hydrogen and helium, the cosmic background radiation, the expansion of galaxies, the structure of the universe on large scales. It also implies that the universe had a beginning. About 13.8 billion years ago, has been cooling and spreading out ever since, may continue to expand forever or collapse, depending on its density and dark energy. The cosmos was no longer timeless. It had a history throughout the 20th century. Astronomers built ever more powerful observatories. Palomar Observatory, 1948, with the 200-inch Hale telescope, Arecibo radio telescope in Puerto Rico, infrared, X-ray, and gamma-ray observatories launched into orbit, and finally, in 1990, the Hubble Space Telescope, which opened a new era of space-based astronomy. These instruments allowed astronomers to see galaxies in the early universe, quasars, powered by black holes, star formation in dense clouds, the slow dance of galactic collisions. The further they looked, the younger the universe appeared. Einstein's equations also predicted strange invisible objects, black holes, regions where gravity is so intense that not even light can escape. At first, they seemed theoretical, but evidence grew. Stars orbiting invisible companions, X-ray emissions from collapsed stars, galaxies with supermassive black holes at their centers. By the late 20th century, black holes were no longer myths, they were common, even central to how galaxies evolve. Astronomers also discovered that ordinary matter, everything we can see, makes up less than 5% of the universe. The rest, dark matter, 27% invisible. But it exerts gravitational pull. Dark energy, 68%. A mysterious force causing the universe to accelerate in its expansion. The universe, it seemed, was filled with mystery upon mystery, even as our knowledge deepened by centuries' end. The history of the cosmos was broadly mapped. The Big Bang, 13.8 billion years ago. Cosmic inflation. The universe expands faster than light. Cooling subatomic particles form atoms. First stars and galaxies. A few 100 million years later, our Sun and Solar System form about 4.6 billion years ago. Life on Earth, 3.5 plus billion years ago. Modern humans, imagi 200 years ago. Telescopes built just 400 years ago. The universe had gone from myth to map. The 20th century did not just change what we know. It changed how we think. The universe had a beginning. It is still expanding. We are made of stardust, the elements forged in dying stars, and most of what exists is unseen. Astronomy had become cosmology, a study not of stars alone, but of everything's time, matter, and the ultimate fate of it all. As the 20th century ended, astronomers had charted galaxies billions of light years away, measured the age of the universe, captured echoes of its birth, discovered invisible forces and unseen matter, found planets around other stars, and begun to ask what came before the Big Bang. But for now, let the radio dishes sleep. Let the telescopes fold their mirrors. Let the ancient light of the first galaxies drift softly across the black. You are a child of that light, a listener in a vast, singing cosmos. The story of the stars is not over, it has only begun. We begin our final chapter not with a telescope, but with a question. Are we alone? For centuries, we gazed at the stars and wondered. But only recently have we begun to answer with data, not dreams. This is the modern era of astronomy, an age of space-based observatories, planet hunters, and cosmic cartographers. And what we're finding is astonishing. In 1995, Swiss astronomers Michel Mayor and Didier Queloz discovered a planet orbiting a sun-like star, 51 Pegasi b. It was the first confirmed world beyond our solar system, and it was just the beginning. As of today, over 5,000 exoplanets have been discovered. Some are gas giants like Jupiter. Others are rocky, Earth-sized, and in their star's habitable zone. Some orbit multiple stars. Some orbit dead stars. And some drift freely through space, unbound to any sun. Our solar system is not unique. Planets are everywhere. NASA's Kepler mission 2009 to 2018 changed everything. By monitoring the brightness of over 150,000 stars, it found thousands of exoplanets, many Earth-like in size and orbit. Then came TESS, Transiting Exoplanet Survey Satellite, launched in 2018, which continues the search with better precision and broader reach. These missions revealed a shocking truth: planets outnumber stars. Most stars host at least one. Many host multiple. Statistically speaking, there are billions of Earth-like worlds in our galaxy alone. With new telescopes, we're beginning to study the atmospheres of exoplanets, looking for biosignatures, oxygen, methane, water vapor, chemical imbalances that might indicate living processes. Upcoming missions, like the James Webb Space Telescope already launched, Ariel and LOVOIR, aim to search for these signs more directly. We haven't found life yet, but we are learning how to look. Launched in December 2021, the James Webb Space Telescope, JWST, represents the most powerful eye ever placed in space. It observes infrared light, letting us see the first galaxies, formed just 200 million years after the Big Bang star birth, hidden in dusty nebulae. The chemical composition of distant exoplanets, colliding galaxies, black holes, and gravitational waves, JWST's golden mirrors, floating in deep space, have already sent back images of staggering beauty and scientific value. It is not just a telescope. It is a time machine. In 2015, physicists detected something never observed before: gravitational waves, ripples in space-time, caused by the collision of black holes, measured by the LIGO observatories. These waves gave us a new way to listen to the cosmos through gravity, not light. Now, astronomy is not only optical, but multi-messenger. Light, gravity, particles, neutrinos, each offers a new layer of insight. Today, we are charting not just stars, but the shape of space itself. The Sloan Digital Sky Survey has mapped millions of galaxies in 3D dark matter. Filaments show the cosmic web. Simulations recreate the birth and evolution of galaxies. We now believe the observable universe contains over 2 trillion galaxies. Each one holds billions of stars. Each star may host planets. The scale defies imagination, but not measurement. Even with all we've learned, 95% of the universe remains unknown. Dark matter doesn't emit light, but holds galaxies together. Dark energy, a repulsive force causing cosmic expansion to accelerate. We don't know what they are, but their fingerprints are everywhere, shaping the large-scale structure of the universe and its ultimate fate. The question returns: with so many planets, with the same elements, with time enough for life to evolve, ... why haven't we found anyone? This is the Fermi paradox, named after physicist Enrico Fermi, who once asked, "Where is everybody?" Possibilities include: life is rare, civilizations destroy themselves, we're looking in the wrong way, or they're out there, and we just haven't noticed. The search continues. Through radio telescopes, space missions, and the faint glimmers of distant worlds, as we gaze farther, we also turn inward toward ourselves. Space exploration is expanding. Robotic missions to Mars, Jupiter's moons, and Titan, plans for human missions to the moon and beyond, ideas for interstellar probes to reach nearby stars at the same time. Earth's orbit is filling with satellites, data streams, and a global skywatching community. The universe has never been closer. Over thousands of years, astronomy has taught us that we live on a planet orbiting an average star in one arm of a vast galaxy among billions of other galaxies in a universe that had a beginning and may one day have an end, has given us tools, technologies, and perspectives. But above all, it has given us humility. To lie beneath the stars is to remember that we are part of something far greater than ourselves. As you listen, as your eyes close and your breath deepens, let this last idea settle. The atoms in your body, the calcium in your bones, the iron in your blood, the carbon in your cells were forged inside stars. You are not separate from the universe. You are a product of its history, shaped by its laws, born from its matter. You are stardust that can wonder. So rest now. The cosmos spins quietly. Overhead, the stars have told their story, and you are part of it.